This is a very active frontier of hadron physics, part of nuclear and particle physics. Again, I repeat that the standard configuration of hadron is like meson with quark, antiquark, baryon with 3 quarks. The exotic hadrons often come with more quarks, like a multi-quark. This is something we call tetraquark or tetraquark meson with 4 quark. 2 quark, 2 antiquark. You can make a color neutral combination out of the 4. You can also make a color neutral combination out of the 5, which carry the baryon number with 4 quark and 1 antiquark. There are also even more exotic configuration like quark antiquark with the gluon. Okay, this is something we call hybrid. And there are more. For example, there are dibaryon, there are pure glue balls. All these have been speculated. In fact, if you look into the literature in the history, the kind of idea of exotic hadron were raised very early, like kind of early 1970s. People started to ask, beyond just the Gell-Mann scheme, are there other exotic hadrons? And over the many years, a lot of experiments have been done to look for those kind of exotic hadrons. Example include, for example, the BAS3 in China, in Beijing, Babar, Bell, Clio, and GlueX, and now we have the LHCb, Atlas CMS, and so on. So all these experiments, have had the capability to look for this kind of exotic hadron, and they have been quite successful. Okay, as I will show you later. Now, so what do we exactly mean by exotic hadron? It's certainly, it's obvious that exotica should not or do not fit into the regular quark antiquark arrangement or 3 quark arrangement. But how do you know that? When you see a particle in your experiment, how do you know this is an exotic one? But there are several ways that you try to figure that out. For example, you can look at the quantum numbers. Typical quantum numbers are like JPC, which J is the angular momentum or spin of that hadron. P is the parity. C is the charge parity. You can look for quantum numbers that are normally forbidden by the typical configuration. To give you an example, here suppose you have a quark antiquark bound state, okay, like a meson, typical meson. Then it's easy to figure out that if you have a total angular momentum J equals L plus S, then your parity is related to the orbital part of your wave function, while the charge parity is related to both the spin and the orbit. So you can easily figure out from this kind of quark model that these are already allowed JPC quantum number configuration for your meson, and these are forbidden. Okay. Now, if you suddenly spot a particle, a resonance that has a JPC to be 1 minus plus, then you know for sure that it cannot be something like a quark antiquark meson. It very likely could be a hybrid. Okay, so this is the one way for you to identify exotic hadron. Sometimes you cannot just figure that out from the quantum number. Then you need to look into the details of the properties. Sometimes you will realize that the properties of your observed hadron are possible only with multiple quark, antiquark, or gluon. As we'll see in the example of the X3872 later. Now, I also want to make a remark here, namely, multiple quarks do not necessarily mean extremely exotic configuration. Here I have an example. That's a deuteron. Okay, deuteron is like a bound state of proton neutron. It has 6 quarks. Now, this obviously is a multi-quark object for sure. But on the other hand, you may say, oh, this is not exotic as I would wish, because we can nicely describe this object as a bound state of just a well-defined proton and a well-defined neutron. So, when we talk about multiple quarks, you should keep in mind that there is a possibility that the object you're looking at may be just a hadronic molecule. Okay, there's nothing bad about it. In fact, remember that the study of deuteron is very, very important in nuclear physics, in particular in the low energy nuclear structure physics. That has been a very, very crucial information to figure out. For example, the nucleon potential like this. Okay. All right, let me continue. Now I want to move on to the heavy quark. So far, I've been talking mostly about the light quark, but in this talk, for the rest of the talk, I will be focusing on the so-called charmed quark sector. Charmed quark is a famous guy in the particle physics and particle nuclear physics. It was first discovered in 1974. There was this famous story and called November Revolution, related to another very famous Chinese physicist, Samuel Tin or Ding Daozhong. He of course discovered this charmed quark from the hadron collider at Brookhaven. At the same time, using electron-positron collider, the SLAC team also found this important resonance for the GPSI. Today we know this is what we call a charmonium. Okay, it's the one example of a charmonium state. It's a bound state of a charmed quark with an anti-charmed quark. Okay, the mass of a charmed quark is roughly on the 1.27 GeV. Okay, so it's very heavy. Remember, this is much like at least a order of magnitude heavier than the stringent quark, and even heavier than the U and the D quark. Okay. So charmonium spectrum, the study of this, has been very important and very useful for understanding QCD force and for understanding the kind of quark antiquark potential that I mentioned earlier. Not only that, in recent years, the CC-bar system offered really unique opportunities for studying the exotic hadron. In fact, till today, almost all the well-established exotic hadron, the famous XYZ states, they're all from the charmonium or charm-containing particle. Okay? So this is a nice chart summarizing, the charmonium spectrum I took from a talk by my colleague, Ryan Michel. So you can see this is the GFPC quantum number. This is the mass. This is the famous GFPSI, which is with angular momentum 1 because it's a vector particle with negative spin parity and charge parity. This is the noise state of the charmonium system, well-known eta C, and there are many more. And the point I want to make is that, first of all, you may wonder why there are so many states. Well, for example, between eta C and GFPSI, that corresponds to two different configurations of spin. One is the spin 0 singlet, the other is the spin parallel between the quark and antiquark. So these are due to the different spin configuration, and their energy difference tells you that the QCD force between quark and antiquark is actually spin dependent. Okay, so that's one way to show you indeed. By studying this, you can figure out something about the QCD force between quark and antiquark. Now, these are like radio excitation. It's just like in atomic physics, you have a principal quantum number for the radio wave function, n equals 0, n equals 1, n equals 2. So these are all the radio excitation. The point I want to make here is that you can see there are particles that were predicted and discovered. There are charmonium particles that are predicted but undiscovered. You can see there are these guys. There are particles that are unpredicted, namely unexpected, but were actually discovered, like this famous guy, X3872. This was the first, discovered and well-established exotic hadron, and there are all these XYZ states. Okay. The point I want to make again with this chart is that we're still far from fully understanding the secret QCD force. Why some are predicted but not found, why some are unpredicted but are actually existing. Okay. So in general, I think this offers, again, unique opportunity for understanding QCD force by studying the exotic hadron. Now, a lot of progress has been made in the just last several years, especially because of the high capability of the LHC experiment. This I took from an LHCb talk. You can see in the heavy Exotica, 62 new hadrons were found at LHC. You can see among these particles, not all of them are exotic particles, but if you look at this labels here, there are the tetraquark, okay, there are the pentaquark. You can see there are all the XYZ states, tetraquark, doubly-charmed, all those states. There are many exotic states, and not only at LHC, many exotic states were also found at other experiments. For example, a couple of years ago, or last year, there was this famous DCS from our BS3 at the Institute of High Energy Physics. Again, the point I want to make is that this is a very active area of study, and many new exotic states are being discovered almost every year. I will focus on for the rest of the talk. I will focus on two of those exotic particles. One of them is the X3872. It was not on this chart because it was first discovered long before the LHC. The other one was only discovered last year. This is the doubly-charmed TCC+. Okay, so let me start with the X3872. 3872 means the mass of this particle, the X particle. It's also known as the chi-C1, and it's actually labeled as the chi-C1 in the particle data book. So you can see this is a very nice plot from the RTCB with high precision data. You can see clearly this resonance peak that point to your our X particle from the GF psi pi pi decay channel. So that's what we are looking at. So it decayed to the fact that it decayed to GF psi pi pi strongly indicate that it had a structure with 4 quarks, the C bar, and 2 light quarks. The mass has been determined, and the weight is extremely narrow. It's much less than 1 MeV. Now I think it has been improved to be like just a few tens of keV, I think. And it's very, very close to the threshold of D0 and D0 star. So that's another very weird property. It's really almost right on the threshold, okay, of decaying to D0 and D0 star bar. The GPT number has been identified as 1++. Now, I remind you that I made the point that sometimes you can use the GPT quantum number to tell you that this is the exotic configuration. Unfortunately, this is not the case for X3872. You look at here, the 1++ actually is possible with just the C and C bar. You could have, in principle, a harmonic state with the same quantum number 1++. Actually, 2 of them were expected from the Quark model, but were never found. They're in the so-called P-wave state in this case. But we know that, or from a lot of study, we know that this guy, is too light and too narrow to be the simple harmonic state. Okay, and from some of the decay channel analysis, people typically believe that the quark content of this particle need to be a C and C bar, and then with 2 light quark, like a U and D bar. The popular interpretation includes 2. One is to consider it to be a DD star bar molecule, and the other is to consider it to be a tetraquark. Okay, this was first observed in 2003 by Bell experiment, and later was confirmed by many other experiments. Basically, it was seen all of these experiments that I mentioned earlier. Where was my like all these experiments basically were able to identify this X particle. Okay, so this solved one question, namely whether a particle like this exists. I think if people generally are convinced that it does exist, then the question is, what is the structure of this guy? As I said, I already mentioned here that there were 2 popular interpretations. One to think of this particle as a real like hadron, okay, 4 quark hadron with very tightly bound CC bar, UU bar, maybe like a typical charmonium with the size on the order of half of a Fermi. Now this is one possibility. The other possibility is that it may be just a hadron molecule, just like the deuteron I showed you earlier. It could be just a bound state between a D star, which is like a U bar C, and D star 0 bar, which is a UC bar. And they interact through the hadronic level interaction like a molecular force by exchanging pion. In this case, because that interaction is actually pretty weak, it's like a van der Waals force in QCD. So this very shallowly or loosely bound, the size of that guy is going to be very large, which may be on the order of 5 Fermi. Okay. Now the interesting thing is that despite nearly 20 years past its discovery, remember it was discovered in 2003. Now we're in 2022. It's almost 20 years. We still could not decide on the final answer with this intrinsic structure. So there's a natural question: can we help resolving the challenge of this quark mass, by using some of our heavy-ion collision measurements? So that's the question I'm going to address later. Another very interesting particle that I'm going to talk about today is the TCC plus. So this was also found by RTCB. I think it was last year. You can see that this is a very nicely identified resonance peak in the shallow of decay product D0 D0 pi plus. Now D0 D0 both include a charm quark, not the anti-charm. Okay, that means this particle needs to have at least 2 charm quarks. Okay, otherwise it wouldn't possibly decay into this channel. So you would have 2 states. Now this is not a baryon, because if it's a baryon, you cannot decay into a final state without a baryon number. So it must be a meson or something like that. So this tells you that it has to be 2 C quark with 2 antiquark, light antiquark. So that's the flavor content. This clearly suggests that it must be exotic. Okay, it has to have at least 4 quarks, CC, U bar, D. The mass of this guy is about 3875 MeV. Again, I think there's a similar discussion about what is the structure of this guy. Is it more like is it a hadronic molecule or not? That has not been figured out. Okay, so I repeat the question: can we help resolving the challenge of quark mass with this, heavy-ion collision? In the rest of the talk, I will show you that indeed there is some progress that maybe shows some promise to help solving this question. Okay, so that brings me to my second part, namely the heavy flavor in heavy-ion collision. Because to produce all these particles in heavy-ion collision, you certainly would need the charm quark. Okay, so let me say a little bit about heavy flavor in heavy-ion collisions. Well, in heavy-ion collision, what do we do? I think in my 2 previous seminars, I already mentioned that more than one time. Basically, we create a very hard gluon plasma. You may say it's a hard quark soup, like in this cartoon picture. We have a soup of quark, and then when that soup starts to cool down, it emits a lot of hadron. Okay, in the end, of course, you see the hadron in your detector. Okay, all these fireworks are like hadron coming out of the collision. So, but inside at the very beginning, there was this soup of quark. Okay, so we have a very hard soup of many night quarks and gluons. U quark, D quark, U bar quark, D bar quark, gluon. All these are available for us to cook essentially hadron, for cooking hadron. Okay. These are some of the plots, like the typical thermal model analysis from, for example, STAR and from also Alice and, both at RHIC and RTC. They showed that indeed our hadron, like especially the light hadron, they're produced from our quark soup in a thermal way. Okay. Now the question is, how about heavy quark? Heavy quark is somewhat different. Okay. The first question is how the heavy quarks are produced. In the case of light quark, what do you do? Well, in heavy-ion collision, basically what happens that beam particle, your nucleus, gold nucleus or lead nucleus, they just dump a lot of energy in the middle of the collision, and that energy quickly turn into your quarks and gluon, and they thermalize, they cool down, they become hadron. The heavy quarks are somewhat different. Actually, the charms are basically entirely produced from the initial hard scattering, which can actually be well described by peak CD calculation. Why is that? Well, that's because the charms are really heavy. Charms can only be produced in pairs. Remember, your initial nucleus or proton and neutron, they don't contain any charm flavor. They only have U quark, D quark, their constituent quark. So collision, you have to produce charm and anti-charm out of lasting. Well, more precisely, out of energy. So you have to produce them in pairs. So the minimum energy requirement for doing that would be 2 times the charm quark mass, which will be on the order of like 2.55 GeV. Well, that's not small. If you think about it, it's like 10 times the lambda QCD scale. It's also about 10 times of the temperature scale of our hard quark soup. If you know the temperature we have here and here, you can see that this scale is like 10 times of that temperature. And with the thermal Boltzmann factor exponential minus 10, that's only 0.000045. So you can see there's almost zero chance for you to produce the charm anti-charm in a thermal way. Okay, so where do they come from? They have to come from the initial hard scattering, and in fact, they mostly come from the gluon-gluon interaction. This is your one proton or neutron, your nucleon in your one of your beam, and this is the other nucleon in the other beam. Each of them will emit a parton, like in the deep in the scattering. You take one parton from this proton and another parton from the other proton. They're having very, very high energy, and they collide through the QCD interaction, become a CC bar pair. And that can turn into gypside, or that can turn into open heavy flavor charm. Okay, so in either case, you can see that that's how the charms are produced. There's another advantage of the charm. When you have a charm in your quark gluon plasma, suppose they're produced, like for example, in this case, you have C quark going one way, C bar quark going the other way, they're not going to disappear, okay? Your C quark cannot just become a U quark or D quark or gluon. So that's good. So it's like a tagging, you know that the quark, once the charm quark is produced from the initial hard scattering, it's going to stay in the system. So my main point is that we have a pretty good idea of how many charm and anti-charm there are in the soup. Okay. You can see that here I'm showing you some sample of a calculation. You do that by doing a PQCD calculation to the leading water. Sometimes you can go to lax leading water. You count how many charm you produce, and you use the fragmentation function, turn that charm or anti-charm into a D meson, and you can compare with the PP collision experiment. Like here, the PP at 7 TeV or PP at 2.76 TeV. By doing that, you basically can figure out, or you can very well calibrate how many charm quarks you produce in the collision. Okay, I actually think it's particularly good because to produce this charm anti-charm, you need a gluon initial longitudinal moment to be at least about a couple of GeV. At rate, that would correspond to the so-called X parameter Birkin X on the order of 10 to the minus 2, but HC it's going to be 10 to the minus 3 for the gluon. And we know that at small x, the gluon probability or distribution becomes very large. So that's very good. Indeed, RHC, the collision at RHC produced a lot more charm quarks and anti-charm quarks than the rake. Now, what happens to the charm once they are produced? Well, you have to consider that question in a few different situations. One situation is that you have a relatively soft charm quark, meaning the charm quark has a relatively small or intermediate momentum. In that case, what happens is that they will undergo a Brownian motion, like shown in this picture. A lot of the surrounding thermal quark gluons keep hitting on that heavy quark. So the consequence of that is that charm quark are going to be pretty much carried by the bulk flow of your fireball, and they will diffuse around the whole fireball volume. So suppose, let's say, it's produced in the middle of your fireball. After some time, it can go anywhere in the fireball volume. Okay, that has been relatively well understood by doing some non-adjuvant transport study. So this is one example from a recent paper I had with Shuang Li. We showed that how doing this kind of transport evolution of the charm quark. Once they are produced from this kind of initial hadron scattering, you take that spectrum, you put it into your a non-adjuvant equation. You can reasonably well describe, for example, the D meson, D stars, and there are A8 or V2. So everything seems to be reasonably understood. So it's basically a diffusion dynamic. For the hard sector, meaning that the really high energy charm quark, anti-charm quark, they are going to penetrate your hot quark soup. The hot quark soup is not enough to stop it. Okay, it will go through the medium, but in doing that, it will lose some energy. So this is basically like the jet quenching business. Okay, it's only that it's for the heavy quark sector. Many studies have been done. Again, the point I want to make by showing you all the plots of RAA of electron decay or D meson or electron decay from heavy flavor, is that we have a pretty decent understanding of what happens for high energy charm quark. They experience energy loss, and then they fragment. They become a D meson, or they decay into heavy flavor electron, and so on. Okay. So how about another possibility? There is actually one more component of heavy quark in the quark gluon plasma, and that's the charmonia. When the quark and antiquark were produced initially, like this, they could just stay together like a little dipole, quark and antiquark. They can move together. They can go through the quark gluon plasma, but that comes with a price because the quark gluon plasma are so dense and so colorful that they're going to screen out the interaction between charm and anti-charm. Okay, so a lot of times that happens. Say you produce 10 cis-bar pair in your initial collision, maybe 8 of them will disappear or dissociate, or sometimes called melting. Okay, so here this is like a typical propaganda for that, namely, depending on your temperature, all these states could be melted. Okay, so that's the melting of charmonium, but some of them will survive. Okay. So you can do that calculation transport study of the charmonium survival through the quark gluon plasma, and you can. And in addition, as calculated at LTC energy, there are so many charm quark and anti-charm quark that you have a like zero chance for regeneration. Then your charm anti-charm, they may happen to be close in the phase space and remake your charmonium at the end of the fireball evolution. So these are some example calculations from, for example, Peng Fei Zhuang and the group, showing you how this can be described. one of the important messages from this kind of study, I think, is that the regeneration becomes important at LHC, especially for low to intermediate momentum region. You can see these are the regeneration which are like dominant in describing the data. Okay, so regeneration means that you have charm and anti-charm that will combine together to become charmonium again. So this is important at LHC energy and for low to intermediate PT. So to summarize my short discussion on the heavy flavor in heavy ion collision, I want to use these two plots from PBM. I really like these two plots, which make a very, very important point. You look at this, spectrum of D0, production, and this is the basically the yield. Similarly for the gypsite. In both cases, you see a very strong enhancement compared with naive expectation from thermal production. You can see these are all log scale. In the case of charm or open heavy flavor, there's a 30 times enhancement, meaning that you have like 30 times more than your thermal model prediction for the D0 production. And gypsite need a quark charm and anti-charm. And that turned out to be 30 times 30, about 900 for the gypsite. So here's the key message. The QGP or quark produced at LGC, which is like 1000 GeV collision, is a heavy doping QGP with a large number of charms. Largely, this offers is on in a certain context, meaning that much larger than the thermal expectation. Okay, so in that sense, I would like to call this quark soup a charming quark soup. First, literally charming means that it's very attractive and interesting, and indeed it's very interesting because it provides an ideal environment for producing heavy exotica. So that brings me back to the topic of producing heavy exotica. So this is the last part of my talk, namely cooking the exotica in our heavy ion collision. Okay. Here I'm showing you some early study back in 2011. Actually, these people, they were studying multi-quark hadron production from heavy ion collision. Naturally, they came to take a look at some of those exotic particles like the X3872. I think to be fair, I think what they did actually relatively simple and crude. They basically used the thermal model production, and then they used a very, very simplified version of coalescence estimation based on harmonic oscillator wave function. But even though the model parameters are not very sophisticated, I think that they showed some interesting message from this study. First of all, the internal structure influenced the yield. So here is like the coalescence production rate divided by the thermal statistical model rate. You can see for some of the particles like the X3872, you can see a water magnitude enhancement in the coalescence picture if you assume X to be a molecule with a relatively large size. Okay, so that does show that the internal structure influences the yield. So that's one important message. Namely, producing the amount of X you can produce in heavy ion collision depends on the structure of that X. That's good news because that's exactly what we want. We want to figure out the structure of the X. The other message I think which is correct is that the hadron molecules are more easily formed. You may wonder why. Well, that's because our QGP has a relatively large volume, that I will show you later. Okay, so I think what really start to generate a lot of interest in studying the exotica in heavy ion collision is because of the first set of X measurements from both the CMS and RCB around 2019. And I think both of these results or preliminary results were first shown at the 2019 Quark meta at Wuhan. Okay, so this is the RGCB experiment showing the X rate or X rate relative to the so-called Psi 2S, which is the radial excitation of the Psi 1S state. You can see a clear dependence on the multiplicity of that PP collision. Okay, so this relative yield depends on the multiplicity of the PP collision. This is the real measurement in the heavy ion collision, the lab collision. You can see the rate between X and the Psi 2S. Again, this is more like a reference, okay, like a baseline, let's say, because it also contains a C and C bar quark. At PP collision, you have that ratio to be about 0.1, where at the AA collision, it's actually a little above 1. You can see there seems to be a very strong enhancement of the X production when you go from PP to AA. Okay, so well, both measurements have not been fully explained, but I think both measurements strongly indicate at a partonic medium effect on the X production. So that's why we got excited right after the Quark 19, and we started to think about this question. Okay, and that two of the paper that we published last year. So these two works are done in collaboration with the team from the South China Normal University. There's the Institute of Quantum Physics or Institute of Quantum Matter. Our colleague N.K. Wang, Qian Wang, Hong Xixin, and their postdoc Hui Zhang and student Yuan Yuan Hu. So we did the two studies, one about the X3872, the other about this doubly-charmed TCC state. I think one of the main messages we try to convey in those two studies is that heavy-ion collisions are really a powerful venue for the massive production and the detailed study of Exotica existence and structure. Okay, so I'll tell you some of the key results from those two studies. The first is the X3872. I already mentioned there are two possible structures. Now we put that structure into the context of heavy-ion collision. So you can see that you produce a fireball like this. There are many light quarks. There are some charm quarks. By the way, I forgot to mention, at LHC, at a most central collision, you could produce as many as the total of 100 charm plus anti-charm quarks. So that's a lot if you think about it. And that's why I keep saying that heavy-ion collision may be the most ideal place for producing those exotic particles. Okay, so if you do have a molecular picture like this, then what you need to produce that X would be a D0 and a D star bar 0 at one, D0 at one place of the fireball and D star bar 0 at another place of the fireball. They're relatively separated when they are freezing out from the fireball, and this offered the opportunity for them to form a hadronic molecule. In the case of a compact tetraquark, then it's going to be mainly produced like all the other charm quarks, like gypsy, like regeneration or recombination for gypsy or Posei 2s. You need the C and C bar to be close to each other on the order of a Fermi, and you pick up also two additional night quark, anti-quark, you form a compact object. This is more like the regular hadron production from the coalescence. Okay, so these are very two different pictures. And I should remind you that the bulk fireball itself has its own size scale, and that can be controlled. Because when you go from a central collision to peripheral collision, your fireball size keeps changing. It can be as large as like 10 Fermi across to as small as just a couple Fermi across. So you really can kind of control the fireball volume. So the compact tetraquark, like this kind of production, would be insensitive to the overall size. It's just like your production of gypsy or production of proton. Doesn't care about the overall size. But it could be sensitive to C and C bar distribution in the fireball, because you need that C and C bar to stay close to each other. Or remember, I mentioned that all these C and C bar, they're going to diffuse around. Okay, they're not going to stay together. Even though they were initially produced together, the C and C bar are going to eventually become far apart because of the diffusion dynamic. This is a random Brownian motion. They are going to move all around. Okay. On the other hand, the hadronic molecule must be sensitive to the source volume, because you need a large volume to start with. If you have a very tiny volume, there's not enough space for you to produce that large size molecule. So these are some general observations. And indeed, we use a dynamical simulation to demonstrate that indeed that's what you will see in a series simulation. Okay. I believe this is the first series dynamical simulation of X production in heavy-ion context. We use the simple model AMPT for the dynamic bulk evolution. The reason why we use it, you can use hydrodynamic, that's fine. But it turns out, I mean, if you really want to produce, for example, a molecule state, the hydrodynamic freeze out is not enough. Remember, hydrodynamic freeze out only care about the mass, doesn't care about the internal structure of your hadron. So that's a drawback that we're still trying to address. Maybe in the future we'll have more dynamic study with the hydrodynamic environment. Now, the initial charm, we use the d meson spectrum to calibrate how many initial charm you should expect in your system. Okay, and then after that, we just let them evolve, and then they will freeze out. For the hadronic molecule, we first form the d meson and then we further use the coalescence of D and D star bar to produce the X. Of course, there are conditions for this in the typical coalescence model. The mass need to match the X3872 mass, and the size need to match the size on the order of 5 to 7 Fermi. We also check that varying this size, from let's say 3 to 7 or 3 to 9 or so, doesn't change the results quantitatively. Doesn't change the result qualitatively. Now, on the other hand, for the compact tetraquark, what you do is that you first form a charm diquark and form an anti-charm anti-diquark and freeze out, and then you use the coalescence of diquark anti-diquark. Again, this is like 2 steps. The condition for this to happen, it depends on the mass matching. All these guys together should give you the invariant mass of your X, and then the size, these guys that are going to coalescence into the X need to be within a Fermi distance. Okay. Now, this of course still is somewhat simplified model of coalescence of the X particle. But the hope is that we use those kind of models to reveal simple yet robust features that distinguish those two intrinsic structures. The most distinguishable feature between the two is their relative size. Okay, the details can be found in the paper. All right, so this is the key result from our study. Basically, between the hadronic molecule and tetraquark, you see 2 order of magnitude difference in the yield. Okay, remember in the earlier study, it only kind of qualitatively showed that there would be a order of magnitude difference. We clearly show that there are 2 order of magnitude difference. But the most important result from here is the centrality dependent. As I mentioned, when you change the centrality from very central collision to very peripheral collision, you are really shrinking the fibrable volume from being large to being small. Okay, so indeed, we see that sensitivity. For the molecular picture, you see that it's almost unchanged at the beginning for the most central, very central, semi-central, and then it suddenly starts to drop very, very quickly when your volume becomes small. Whereas for the tetraquark picture, you don't see much dependence on the centrality. So a strong volume dependent of hadronic molecules. This scenario would also hint that RAA, namely if you compare your X production in MATLAB with the proton-proton, you should really see a strong enhancement with RAA much larger than 1. Okay, so that's what we would expect. All right, so another important feature I want to point out is that this is likely where the fibrable size becomes smaller than molecular size. That's why the yield starts to drop very sharply. So in the future measurements, for example, with CMS or ALICE, if one can map out that centrality dependence and see this kind of dropping behavior, that's really like nailing the size of the X3872 particle. So that I think is very, very exciting. Okay, so we also studied many other heavy ion observers for this X particle. You can see there are centrality, there are the rapidity dependence, the PT dependence. We also calculate, elliptic flow V2. Well, it's perhaps difficult to measure, but maybe with the LTC Run 3 and future upgrade, it might not be entirely impossible. But if one can measure this, that also help understand the nature of X3872, whether they are part of a thermal or nearly thermal bulk matter, or there's something different. In the paper, we conclude that it's tempting to envision an exciting time of vibrant and coherent theory and experimental efforts for exploring the heavy ion collision of massive production factory of exotic hadron. Okay, so I think that's very exciting. And last year, LGC found this new particle called TCC. Well, TCC, as I already mentioned, they must be exotic. They must have at least 4 quarks, C, U bar, D bar. In fact, because of those 2 light antiquarks, they have, they each are like isospin doublet. Remember, U, D are isospin doublet. So in this case, if you combine the U bar and D bar from an isospin point of view, you could have a singlet state, or you could have a triplet state. Okay, it's like a U bar D bar, or U bar or D bar D bar, and so on. What RGC is discovered is most likely this TCC plus, with one positive charge, which is the isoscalar or isospin singlet combination, okay, in this channel. In this case, for the TCC, I think heavy ion collision, as we argued in the paper, heavy ion collision have even more advantage for the production, because this guy, to produce this guy, it requires at least 2 pairs of CC bar. So that's even more difficult than the X particle. For the X particle, in the initial hard scattering, you need only to produce 1 pair of CC bar. Now, in this case, because you need at least 2 C quarks to make this hadron, so in the initial hard scattering, you would need to produce at least 2 pairs of C and C bar to start with. That's why it has been very, very difficult to find, of course. But in heavy ion collision, we don't have this problem. As I already mentioned, in the central heavy ion collision at RHC, you have like almost 100 charm and anti-charm together. So that's really fascinating. So in this paper, we studied the production hadronic molecule picture. Again, we expect a strong volume effect because of the molecular structure. And we also expect an even stronger threshold effect when you go to the peripheral collision. The reason is very simple, because again, you need at least 2 C quarks. When you go from central collision to peripheral collision, your binary collision number, which controls the initial hard scattering, become very, very sharply dropping. So at some point in your peripheral region, you wouldn't be able to produce 2 CC bar pairs on average. That's where you basically would have 0 chance to produce a TCC. Okay, so that's different from X particle. So in our simulations, indeed, we see that behavior. So this is the yield of the TCC of the function of centrality. You indeed see a very, very sharp dependence on the centrality, and that centrality dependence is even stronger than the X particle. In the lower plot, we show the TCC to X3872 ratio in the same simulation. You can see that in the central collision, their production rate or yield are comparable. But when you go to the peripheral collision, it drops down very, very quickly. So when you go to peripheral region, the TCC is much more strongly suppressed than X3872. Again, that's because of the threshold effect. At some point in the relatively peripheral collision, you wouldn't be able to produce enough charm quarks. Okay. So in other words, the TCC is even more sensitive to how many charm quarks you have in the system. Okay. We also computed the elliptic flow. It looked like that in the molecular picture, the elliptic flow of the X and TCC are basically comparable. Okay. So that's all I want to tell you. So that brings me to my summary of this talk. I hope I convey the message that study of exotic hadron is an important frontier of QCD physics with the many unsolved puzzles, like different structures or the existence of exotic states. Heavy ion collisions at a very high energy, like the RHC energy, proved to be an unparalleled factory of producing many charm quarks and anti-charm. As I mentioned, very large number of charms. And these can be used for producing heavy exotic states and measuring their properties. Heavy ion fireball sites serve the runner, basically, for calibrating the intrinsic side of exotic states like the X and TCC, as I showed you in our results. Okay, so eventually, if these are measured, centrality dependent measure, we're basically measuring the size of those exotic states. Future measurements, I think, will be very exciting. I think I've been, interacting, communicating with, our experimental friends at ALICE and also at CMS. My understanding that from the run 3, there will be a lot more data. The RHC run 3 for the heavy ion will have a lot more data. Right now, CMS measured about 100 of those X particles. Maybe with the run 3, that can become many thousand. In that case, measuring a centrality dependence perhaps will become feasible. And also, future upgrade of ALICE, high luminosity, RHC, and so on, they may, provide, unique insights into those exotic. So I think this naive expectation is really just starting. Okay, so many questions need to be answered and need to be studied. And that also brings me to the end of my series of seminars. I want to repeat the point I made earlier, namely, there's still a rich and diverse heavy ion physics program onward. By tuning beam energy from very low energy to very high energy, you can access different, novel dimensions of QCD universe. At very, very low energy, you can study the polarization, vorticity, and polarization. at intermediate energy. There are interesting effects like the current magnetic effect and other magnetic field driven effects. At a really high energy, there are very interesting, exciting questions about charm Exotica that one can study. So with that, I will stop here and thank you very much for your attention.
好，谢谢金峰，今天详细为我们介绍了这个利用这个高能重离子碰撞来研究这些X3872 TCC 最新的进展，这为我们提供了这个研究这个奇特粒子态的一个新途径。下面进行这个提问交流，有提问的请大家举手。好，旭光。
哎，好的，金峰啊，非常有意思的一个报告。那个23页，我看有2个实验的图。对，对，左边这个是 LCCB 的，从这个 LCCB 的结果呢，我们看它的实验结果好像说，随着多重数的增加，如果我们看这个，我不知道这个红色的点，它是随着多重数增加，这个产生截面是在减小，是吧？就是这2个 X，
对，它是
就是这个 X 和
这个
和 的比，对，
你看到就是这个，
但是右边，对，我的问题是，如果看右边这个 CMS 的结果，在 PP 碰撞中的这个产生截面的 ratio 是比这个来的碰撞中的要小非常多的。这个 trad 是不是跟左边这个不是一致的呀？就是我如果把左边这个多重数的 trad 一直向上走到这个重离子碰撞的阶段。
very good question。对，我首先解释一下，这个的话就是相当于这个是 average， 就 typical PP event。这个 number 呢，应该跟这个 number 基本上是一致的，它们是 consistent，就是这些 event 你不要看它画的这个，但实际上当你 go to 这个 high multiplicity， 这些 event 的数目是非常少的，就这个是更 typical 的 PP event， 所以这个大概接近 0.1 呢，跟这个 CMS 是 consistent。那你现在看这个 multiplicity， 随着 multiplicity 增加，你可以看到 relative 的 percent 2s 的话，它的 ratio 它的产额的话是先降低的，但是这个图实际上画的有点模糊，实际上你到这个地方你看到100以上的时候，它实际上是转过来的。那么如果你 continue 这个图，这是一个很好的问题，它会怎么样呢？到 LTC 的话，它会上来，到那个 LED
实
际上对，昨天洪许可能也在这里，我们还在交流这个事情，洪许指出来就是说在这个 Quark matter 报告里面，实际上现在有新的结果，已经有了 PLED 和 PLED 的结果。那么你确实可以看到这样一个趋势，就是先下降后上升，
就上去了。真的是这样。
对，
这很有意思。
而且实际上还有一个 point I want to make， 就这个点就是说这个只是 count the raw 的这个3872和 2s 在那个实验里面，实际上呢这个还没有 take into account 这个 Brown-Chern ratio 的 difference。实际上如果 take into account Brown-Chern ratio difference， 这个点可能还要往上 jump 很多。OK，anyway，这个不是 official 的这个 result， 我只是告诉大家有这样一个 information。
很有意思。好，谢谢。
好的，下面请那个马龙提问。
好像没有听到问题。
对，他好像是没有听到。我记得就我问一个问题，就是你前面提到了，就是我们这个，比如说接普赛啊，还有这些开 C 他们这个就有一个得败屏蔽的问题，是不是？那么像这个3872，它这个4夸克带和分子态，它受得败屏蔽的影响是不是不同的？
对，你这个很好的问题。如果说他们是在这个比如说在高温阶段有形成的话，那么它是不可能生存下来的，因为这个他们肯定是比这些态都还要更容易被融化的，所以他们不可能在 QGP 项来形成，他们只能是说在强子化的时候才能够形成。对， 那么呢，同样的，这也有一个我想你想说的意思就是说，这两个不同的结构的话，它们是不是这个稳定性不一样？这个呢，现在这个问题研究的有人研究的不多，但是呢，总体来说呢，我觉得可能是那个分子态的生存能力，如果说把一个分子态放在这个强子气体里面，或者说把一个井质态放在强子体，那么可能这个分子态的话是更容易被打碎一点，就是说，但他们的 QGP 项的话可能都不会存在。
好的，那强子项它有这个强子末态的相互作用，会不会也会把它打碎掉呢？
对，这个是一个很好的问题，这个有一些人研究，但是我想在我们这个工作里面的话，我们没有去具体的去分析这个强子项的影响，但是呢，这个应该说是一个很好的问题，这也是为什么说就还有很多问题需要去研究。那么这个形成了以后，他们到底这个后面会不会受到这个强子气体？当然，它是一个相对来说比较稀薄的气体，但是它仍然有可能跟这个粒子产生末态相互作用。那么这个呢，需要在未来的研究里面把它包括进去。
好的，明白了，谢谢。那个黄焕东老师有问题，黄老师，请您提问。
Jin-Feng，谢谢，very nice talk。So，
你好。
那个，因为假如我们去看那些 exotic 的质量，因为它的质量就是在这个D star 这个 threshold 的这个低一点点，所以从质量来说，它就不能够是个 deeply bound 的 quark state。但是为什么你就什么样的图像你认为它还是可以是这个 deeply bound 的 quark state？
这个呢，原则上是有可能。你看啊，它的质量是3871。假如说我们考虑一个 tetraquark，两个 C 的话，就 C 和 C bar 的质量的话，加起来的话大概是2500多，对吧？然后呢，加上两个氢的quark，如果说我们300多的这个 constrained quark 的话，那就是600多，3100多。那么这个的话呢，就是它仍然就是说有可能是这个就是说像我们说更像一个 normal hadron 的一个 bound state， 这个是原则上是可能的。现在这个东西就是说这个
但是它这个 state 它的这个quantum 就是 1++ 已经测量的，这个是确定的，对不对？
对。
所以这个确定的话，那就是说它这个里面的这个那个 quark， 就是它一定要就满足这个条件的话，就是因为只有 D 和 D star， 因为才能够就是造成这么一个就它内部的 quark 的这个 correlation， 它一定要满足这个条件的话，可能就会有一定的这个 constraint on 这个quark 的，就是 diquark 的这个 mass 在那里。
对，这个我完全都同意啊。这个实际上就是就像我说那样，强子物理的人已经研究了10-20年了，就是他们还是没能讨出一个结论来。它这两个模型呢都有它的各自的道理，就是说，从我个人的观点啊，因为就像你强调的一样，这个 near threshold 是一个非常特殊的性质，就是说它跟那个 D0 和 D0 star bar 的这个 threshold 这么靠近的话，它们的 quantum number 又是吻合的话，那么从量子力学的角度来说，它们必然会有 mixing， 就是说这个是不可以避免的。所以从这个角度来说呢，它的 wave function 必然会有一些 hadronic molecule 或者说 large size 的 component。但另一方面，这个问题可能是说，在它的 short distance 上，它可能更像一个 tetraquark， 因为整个 wave function 它可能有 short distance behavior、long distance behavior。那么现在问题可能也许最终的结论可能既不是一个简单的 pure 的 hadron molecule， 也不是一个 pure 的这个 tetraquark， 它可能也许是两种的某种混合，对吧？就这是一种可能的解释。因为他们这两种模型都可以解释一些不同的方面，但是没有一个模型能够解释所有方面。
对 ，OK，that's OK。So， 另外一个就是因为你这个 predict 这个那个 centrality dependence 的话，主要是 based on 是这个weakly bound 这 molecule state 还是 deeply bound quark state， 对吧？是这个。那么，对，那从这个模型 scenario 去出发的话，那么你应该这个预言这个像 deuterium， 因为 deuterium 肯定是 weakly bound， 就类似于你 weakly bound molecule state， 对不对？ 那么假如你预验这个 deuteron 的产额随着这个 centrality 变化的话，因为我不知道这个数据是符合你那个这个 molecule state 的 prediction 吗？
这个我们没去算，但这个是完全可以算，而且可能搞不好已经有不少人已经算过这个 deuteron 的 production， 包括 light nuclear。那么 deuteron 的话呢，我实际上说的这个非常有意思的 particle， 它也不是很 tightly bound， 但是它的 size 的话，可能没有我们想象那么大。它的 size 我有点不记得，可能是马老师其他就比较熟悉这个 structure， 我印象中是2.几个费米，就它的 size 就不是像这个 molecule 有5个费米那么大，所以它呢。你可以想象，就是它肯定有一定的 size dependent， 但是也许没有这么 dramatic， 有一种可能性，因为这个完全取决于你这个 size 有多大，对吧？我印象中 deuteron 可能是2.几个费米。
对，几个费米。对，但因为它也是就是才2个 MeV 的 bound energy。
对。
这个 deuteron 的 effect 那个 LHC 已经测出来了，就是它就是 deuteron。比上 proton 的 ratio， 它随着那个 multiplicity 降低而降低，就包括那个 helium 碎，然后还包括 hypertriton， 他们都已经测出来了，就是定性上跟你算的这个是类似的。但是呢，
对，这个从那个 picture 角度应该是这样，就是如果有 volume dependence 的话，
对，但是缪老师是这样的，是因为我算了很多，我是顺开家，我算了很多那个light nuclei， 就是 anis 各种 system， 从 pp 到 pled 到 led， 对于多种来说呢，通过 coalescence 计算和那个实验上呢给出来的这个 suppression 的话，大概是2倍左右，就是说 pp 的里面的相对于 led 它的 suppression 大概是 factor 2， 然后对于这个 helium 碎呢，它大概可能是4倍，就是4倍，然后对于这个 hypertriton 呢，他们现在最新的实验数据应该是大概在1个量级，就 hypertriton 一个中子一个质子加上一个 lambda， 然后它的这个 radius 大概是5个费米，然后呢，通过 coalescence 计算的话，大概在1个量级，就是说可以它的 suppression 的话可以就是说相对于 led 的话，大概会有10倍的这样的一个 suppression， 这个他们实验上已经测出来了。但是我想 mention 一个事情，就是说对于这个 suppression 的话，现在其实有2种解释，一种的话是用 coalescence， 就是说它的这个 large size， 就是 molecular state large size， 另外一种呢，还有一种你知道在那个statistical model 里面，他们有一个 effect 叫做 canonical suppression。canonical suppression 就是说，你的这个碰撞里面的话，它是一个 canonical ensemble， 就是说它的
化学不平衡是吧？就是说你引入了一个，比如说 fugacity 这样的方式是吗？
不是，是它的 charge 是严格守恒的，就是因为它的 charge 就是说你 heavy ion 对撞的话，它是一个它的 baryon charge， 它是一个严格守恒的系统。这个效应呢会导致在 small system 里面呢，他们有计算也会产生一个 suppression。那么
对
这个 suppression
这个就像我刚才说的，可能有点像那个 threshold 一样，就是你需要足够的 baryon number 来对，这个我同意啊。就而且这2个效应从某种意义上并不矛盾，对吧？他们都可以贡献到这样一个 suppression 里面。
对，所以就是说你如果观测到这个 suppression 的时候呢，你可能还要可能还不能直接 claim 说它就是一个
OK
可能有一些其他的 effect。
我明白你说的意思的，但这个fortunately 就至少对 X 来说的话，它可能就是说不会受到这个 charge conservation 的这个 suppression， 对吧？我完全同意你说的关于这个 baryon number 的这个。
对，这个是我们研究亲和里面就是大家最近一直在讨论的这个问题，就是它这些 suppression 的话确实是观测到的，但是它的这个产生机制的话还有挺多讨论。另外一个是关于我还有最后一个这个问题，就是关于这个 hadronic 的影响 hadronic phase， 因为你这个 molecular state 的话，它的 binding energy 是0.1个 MeV 是吧？然后对于 deuteron 来说的话，它的 binding energy 的话是大概是2.2个 MeV， 然后有很多计算就是说 它这个 deuterium 的话，如果放到 hadronic phase 的话，它其实90%以上的话的 deuterium 的话，它都是不能 survive 的。它90%以上都是来自于 hadronic 的相互作用，就是说你如果QGB 强子化产生一些分子态，那么90%以上它是会被打散的。这个就是现在有很多人做了一些计算，发现大概是这个样子的。
对，这个可能是一个重要的一个需要 take into account 的 effect， 我完全同意。就是这个取决于，比如说我们这个 fireball 里面首先产生的 D0 和 D0 star bar， 对吧？但是这些它不会完全消失掉，它们在火球里面氧化的话，这有2方面，一方面是比如说在相对早一点时间形成的 X， 它就像你说的，它通过hadronic interaction 也许又散掉了。另一方面呢，这个 D star bar 呢，它们在系统里氧化呢，也许呢有一些呢是在比较晚期才达到这个复合或者 matching 这个 condition， 那么它们也可以形成，对吧？就在整个 hadronic evolution 的过程中，这个效应呢，这个确实需要做 dynamical 的这样一个计算呢，才能够最终的来确定到底是怎么样，对吧？但是这个呢，从另一方面来说呢，我觉得就是说这个 size 或者 volume dependence 还是一个比较 robust 的 feature， 就即使 take into account 的话呢，那么也许把这个 yield， 也许比如说像你说往下 reduce 的一个 water magnitude， 这是有可能的，对吧？那么但是呢，那个volume dependence 可能还是相对来说比较 robust， 这是一个。第二个呢，就是说，刚才我也提到了这个 data， 这个 data 呢，就像我们说的，如果说假如说这个没有这个 hadronic interaction 呢，也许这个我们也许 predict 的这个 RA 或者什么可能会太大了，也是有可能。就是那么这个呢也未见得是个坏事，就是说你相当于说有一定的 hadronic phase 的 effect。我觉得这个很好的课题倒是，对这个将来的话，我们肯定是需要把它搞清楚。
是的，对，就是我们现在研究这些 deuterium helium 这些 molecular state， 它的这个产生机制，就是这个 hadronic phase 的这个 effect， 现在就是很多人在做研究。我觉得您算的这个也是类似的，就是您如果最终要跟实验进行 compare 的话，这个 hadronic effect 应该是一个很重要的 effect。但我也同意你说的那个，如果它的 size 是5个到7个 fermi， 那么它肯定是会有，它对它的产额的话肯定是会有影响。对，好的，谢谢您。
好的，谢谢你。
好的，那个何敏老师举手了，何老师，请您提问。
金峰你好。
哎，何敏你好。
你好，谢谢你们 very nice talk, very nice work。但是我一直有一个疑问，就是你在这个 AMPT 里面做这个 X particle 的这个产生，你分2步，第一步我详细读过你们的这个 very nice paper， 第一步你们先做这个这个 coalescence quark coalescence， 就是一个 C quark 加一个 Q 到 diquark， 或者 C quark 加一个 anti-light quark 到 D meson 或者D star， 这是第一步。第一步这2个方案没什么区别，因为 diquark 和 D meson 它们都是 bound state， 都是这个 radius 都是on the order of 1 fermi， so no difference for this step。然后第二步你们再做一个 two body coalescence， 就是一个 D 加一个 D star， 变成一个 molecule， 或者一个 diquark 加一个 anti-diquark 变成一个 tetraquark， 是吧？ So effectively you are doing just two body coalescence in the 2 scenarios, molecule or tetraquark effectively。但是在第二步的时候，这个你们是在这个 AMPT 里面做 coalescence， 但还是 coalescence， 还是这个 TCCM 的这个柯老师的 coalescence， 这个 instantaneous coalescence model。第二步的时候，你们这个我看过你们的文章里面，这个 invariant mass 这个 two body coalescence allowed invariant mass range almost the same in these 2 scenarios， 就是形成 tetra， 就是 diquark anti-diquark 形成 tetraquark， 或者这个D and D star、D and D bar 形成这个 molecule， 这2个 coalescence scenario 它的 invariant mass range allowed almost the same。I remember。 这就意味着他们的这个两体 two-body coalescence 允许的这个 delta p， 就是这个动量的不确定度，这个两体的动量的不确定度范围是一样的，几乎是一样的，因为你这个 inverse mass 的范围是几乎是一样的。好，这是一方面。但是另外一方面，我们知道这个做这个 coalescence， 比如柯老师的 coalescence model， 这个 Wiegand function， 你们这个 AMPT 里面你们没有明确的显示这个 Wiegand function， 但是它有 already implemented in the AMPT I believe。这个 Wiegand function 它有两个，一个是 delta x， 一个 delta p。delta p 就是动量不确定范围 ，delta x 就是这个两体的这个空间范围的空间的不确定度。这个 delta x 乘以 delta p of course 它应该满足这个 uncertainty principle。现在你这个 delta p 在这两个 scenario 里面，这个 delta p 几乎是一样的。所以你就只剩下你的这两个方案得到的结果的差异就只来自于这个 delta x。但是我知道，如果你这个 delta p 是一样的，你看这个 coalescence 这个 formula， 那得到的结果就会正比于这个 delta x 的立方，也大概就是这个一个两体的 bound states 它的 radius 它的半径的立方。好，现在你看你这个你一个是这个 tetraquark 是1个费米，它的 radius， 它这个molecule 是比如5到6个费米，它正比于这个立方，这个 radius 的立方。我把它立方一下，5除以1就是5的立方就是125，6除以1，6的立方就是216。所以我一看我就几乎就能够看到，如果你这个 delta p 就是 inverse mass range， 也就是 delta p 是一样的，那这个差别，它们的场合的差别就一定会是100到200的这个量级。我的理解对不对？
这个大致上主要是一个 size 的 difference， 对，就是说实际上在这个我不知道，就是你是指的这个柯老师这个 coalescence 的这个具体是就这个是在什么意义上？但是就是说在 AMPT 里面的话，你如果但是我们用的都是从那个紫薇那里拿过来的。
对，就是那个。
对，它这里面呢，它有一种呢，就是说你可以用 Wiegand function， 就严格意义上来说呢，你需要做的是用Wiegand function， 对吧？去计算这个phase space 的这样一个 convolution。另一种呢，实际上在紫薇的相当一部分的计算里面呢，实际上是一个更简化的一个方式，就是说你的质量当然要 match， 对吧？你比如你要产生一个 proton， 当然你的质量必须要 match proton 的质量，对吧？那么呢，然后呢，这几个parton 它需要在一定的这个相空间范围内，这个相当于你可以认为是一个就像一个 hard cut off 呀，就相当于说你对 wave function 你没有很 detailed information， 因为如果你要 rigorously 做这个 Wiegand function， 你需要知道你需要形成的 hadron 的 wave function， 这个呢没有人可以严格的定出来，就是说很多时候呢大家用 harmonic oscillator， 但这个东西你说有多准，这个未见得比一个简单的 size 更准一些。这是一个 question mark，OK， 你比如说对于 X 来说，不管是 molecule 还是对于这个 tetraquark， 就是说紧质态，它的 wave function 做强子物理的人也不是很清楚，对吧？那么你就没有办法说我用它来做一个严格的Wiegand function 的计算。那么呢，我们这个里面呢，就是说具体到这两个 scenario 呢，你的理解基本上是准确的，就是说 mass 当然需要 match 到 x3/72的 mass， 对吧？因为它们的总的 inverse mass 必须是，要不然那不可能形成一个 x。另一个方面呢，它们的主要差别就是说，在这个 size 上面，我们在这两个在做第二步 coalescence 的时候，当然这个还有一点微小的差别。你比如说，你这个 C 和一个 antiquark 形成一个 D0 的话，它需要在 D0 的 mass 范围那个范围上，对吧？那么呢，如果是 diquark 呢，那么相应的它们俩需要形成在一个 diquark 的 mass 上面，所以这两个呢还不完全是一样的。所以呢，就是说，然后呢，第二步呢，就是确实像你说的，就是我们在进行第二步的 coalescence。大致上来说，这个主要确实是一个 volume effect， 像你说的，就是说，是一个 size 或者立方的这样一个效应。但是你也看到，比如说在这个结果里面，你可以看到，如果你的 source， 你的 fireball size 太小了，那么它就会对这个 molecule state 有一个很强的 suppression 的 effect。你看到到后面它比这个 tetraquark 的场额还要低，那么这个就是说你可以看到，这个确实是由一个size 的效应带来的。
对，这个 size OK， 这个 size dependence OK， 我相信如果是这样做的话，一定会有这个 dependence。但是我刚才的疑问是，我不讲这个 size dependence， 我就是比较这个 molecule 和这个 tetraquark 的 coalescence， 这个 two-body effectively two-body coalescence。我的意思是，就是即使在 AMPT 它这个数值的解法，它也是基于这个 coalescence 这个 formula 这个在这背后一定有一个类似于 Wigner function， 也就是说一个 delta x 一个 delta p 这样的限制，而 delta x 乘以 delta p 应该满足这个 uncertainty principle， 应该等于 h bar。就是如果你 delta p 是一样的，那 delta x 应该是不一样的才对。现在就说
我不
delta x
确
不一样，delta
定这个
p 就应该
里面的话，
不一样。
这个 delta x 的，当然我没有去仔细看它里面的 delta p， 这个我不但是这个那未见得它的 invariant mass 是一样的，不见得代表它的那个 momentum spread 是一样的，就在 central mass 里，这个不一定的。
为什么不一样？
我可以说一句话吗？就是这个产生这个 x 的，它不是零温的，就是它是一个有温度的，是大概是155或者是160左右的时候产生的这个 x， 不是零温，所以它那个 uncertainty principle 那个应该是要修改。
为什么要修改？你做两个
delta
你当然
delta x 乘以 delta p 它不是h bar 了，它应该是换一个东西，用那个就是 Wigner function 定出来的，但是 Wigner function 我们又不知道它是什么。
不是 Wigner function 定出来的，它是 Wigner function 的一个 constraint。
另外一个，我想跟你我想指出来就是说delta x delta p 的 h bar 只是一个 lower limit， 它可以是任何比 h bar 大的值，就是你也不要认为它一定要是 h bar。
是。但是我说在这两个 scenario 里面，他们应该满足同样一个 uncertainty principle。
因为我们没有我刚才说了 uncertainty principle 只是说 delta x 乘上 delta p 大于等于 h bar， 并不代表它一定要等于 h bar。
OK，
好的，由于时间关系的话，我们还有一个问题是那个马龙那个他设备有点问题我那个转述一下，因为他是做那个地埋葬的，所以他的那个问题是关于那个就是是否在28页的时候，他担心就是说，就是这个地埋葬的中心度分布和这个实验是否一致？这个就是说和实验的差异是否可能会造成这个对这个组合态的这个中心度这个趋势有没有影响？我理解它是这样一个问题。Jin-Feng。
好，我们的话应该是在几个不同的 centrality， 有看过这个低埋葬的这个 spectrum， 就是和这个比如说是2.76个 TeV 的这个历史结果去比对过。这个当然主要是为了我们 calibrate 我们初始到底有多少个 C 和 C bar 在里面。我印象中的话，应该是基本上还是吻合的，就是说，当然我们可能没有 check 所有的 centrality， 这个有可能。应该是这个问题是吧？就是说他的应该问题是说我们有没有，
因为他在 STAR 上面是做这个地埋葬的这个 spectral 的我觉得他应该是这样一个问题。
这实际上是很好的问题，就是我刚才实际上在开始讲这个 heavy flavor physics 有提到，当然就将来来说的话，如果说希望有一个更好的模型的话，那么就是说按照我们标准的做法，就是说做这个 heavy flavor transport， 那么呢，然后呢再把这些 heavy quark 去做 coalescence 去形成的 x， 那是我们将来的一个目标吧。因为这些的话都有很多的 measurement 可以去 calibrate 你这个 charm diffusion 的这样一个 dynamics。你原则上说，你初始放进去 charm quark 和 anti-charm， 让它氧化到最后，那么你 implement 这个 coalescence 来计算它那个能形成多少 d 啊 d star 啊，能形成多少的 x。对，这个可能是我们将来要做的一个事情。
好的，那个马龙也回复了，说他理解了，就是这个问题。好的，那个，马老师，
对，这个报告很有意思啊，这个，
谢谢。
就是刚才大家也讲到了这个有限温度跟零温，包括这个结合能啊什么。我在想，在低能的时候啊，它当然能量低的时候，这些其中有一个叫 motor 这个相变，或者叫 motor density， 就是说我们考虑氢核产生的时候，在非常低密度的时候，它的结合能跟温度啊，跟这个密度是有关系的，对吧？那么这个就是这套东西啊，在目前，比如说你说这些像这个斯夸克态啊，这是分子态，它产生应该也是比较末态的这个时候，对吧？
对对，
就是应该不是就是你说刚才也不是柯基 P 那个项的这个时候，应该是木态的时候。木态的时候，当然它是那个密度不像低能里面这个密度怎么低，但是呢，我在想这个像这些这个模特这个 density 啊，在这里面像这种高能的重离子碰撞里面，不知道有没有影响？就是说研究说这个结合能是跟温度跟这个 density 是相关的。那这样的相关性的话呢，会导致这个当然这个一些产额啊，可能这个就分子态跟那个呢也会有所不一样，对吧？当然我们现在这个结合能啊这些因素里面，在 coalescence 里面都摆进去了，这摆进去呢都是一个定态的一个静态的，是密度这些的温度是不依赖的，这样的一个东西，对吧？
对对对，是这样的，就是现在就您的意思是不是说像就比如说我的 X 的这个包括它的结构甚至它的质量，
对，
在有限温度密度环境下会发生一定的变化。
没错是，但是我们现在coalescence里面摆进去的东西都是一个 fix 的一个结合能，
对，
比如说像高吧，就是说对吧？
是的，我们现在用的都是相当于是真空性质吧？可以，您的意思可能就
对。
这倒是一个很有意思的问题，没有从这个角度去想过。这个确实是一个有意思的问题。就比如说，在这个咱们就说强子环境吧，就是在强子环境里面，现在有一个有限的温度和密度，那么它这个结构和质量啊，包括就是从结合能的角度来说，相当于就是质量的话，那么随着这个如果变化的话，确实会对它的形成肯定是有影响。这个问题确实可能还真的没有去仔细考虑过这个问题。对，这倒挺有意思的一个问题，可以将来我们可以研究研究。
是的。
这个原则上是可以做的，就是说相当于说，
对，因为在低密度状态方程的时候，它这个是很明显的，就是特别是那种非常这个稀薄气体的时候啊，它这些结合能啊是完全相关性是非常大的。但是在高温这样的一个情况下，这个密度到木态的时候，你说它密度实际上也不是很大，对吧？这个我不知道，反正至少可能也是会有影响的，就是
对，它是有一定的温度密度。这个实际上跟刚才之前有几个问题也都是相关的，就相当于说，在这个强子下，因为这些态的话，可能只会在强子下形成，那么形成了之后，它怎么受到这样一个强子环境的影响，就是说仍然是一个有限温有限密的这样一个环境的影响。那这些影响呢，可能会影响到它的产额和分布。这个确实是将来应该还值得进一步去做的一个问题，就是说咱们就是说现在只是说估算了一下它的直接从这个里面产生出来能有多大的产额。那么第一来说，这个结合能啊和这个质量的变化会不会影响这个产额？然后呢，它到了这样一个环境，它能不能生存下去？这都是我觉得都是挺有意思相关的问题。对。
因为相当于你现在，比如说你这个分子态也是形成了，对吧？你这个分子态这个概率那个产额要比斯夸克态的都高很多。但是你刚才也说了，这个就是很容易打碎。那么这个阿弗德伯勒这个假如接上去，那到底木态的时候，你这个分子态打碎了之后，这个你从什么样的角度，这个探测的角度跟斯夸克态形成探测的这个角度到底相差多少？这个可能现在也没有定量的进行研究，对吧？
是的，这个完全同意。这个很好的一个课题，咱们可以接下来就进一步研究，就在这强子环境的影响。这个确实是我们目前的话都是用真空信息，那么它可能强子在这个热密环境的话会有不一样，应该有不一样。对。
好的，谢谢。
好的，
你这3个报告都讲的挺好，反正这个
谢谢马老师。
这个第一个是关于这个守正磁效应的，这个是当代高能重离子的热点。接下来又是关于这个转动跟极化的。今天呢，我们也刚刚把一篇 STAR 的文章，关于这个自旋排列的文章放到 archive 上去了。这个也对吧？也类似。
是那个 spin alignment 吗？就是
对 spin 呢，就是 phi 跟 k 的，刚刚放到 archive 上。昨天那个谁也讲了报告了嘛？
对，实际上这个跟这个图有点像，对不对？就也是到低能往上一直跑。
对，是的，是的。
这个非常有意思，这个我觉得现在还不太好理解到底为什么还一直往上涨，反正是挺有意思的课题。就是我觉得这个也挺好，就是这个通过这样一个这个 seminar 平台，大家讨论交流的话，也给我们提出了很多新的有意思的问题，可以进一步的研究。
谢谢。对， 这个还有就是说，这个现在的确重离子，像你今天这个报告里面完全体现了这个重离子跟这个粒子物理这个领域的一些交接了，对吧？关于这个奇特强子态这个。
对，这应该说跟对强子物理、粒子物理是有交叉的，对。
是的，好的，好，谢谢。
谢谢马老师。
好，那谢谢金峰这个3讲给我们介绍了这个关于这个就是我们强子这个物质里面的这个一些新奇的这个现象啊。然后金峰辛苦了啊，
没事，
我们期待对下次能和你面对面的交流啊。